Okay, hello everybody. We started to talk about the empirical part you should do in your term paper, and within this, hopefully we see it in a minute on screen. Yeah, we were talking about the output gap. I think some guys were also in the lecture today in macroeconomics. There, we also talked a little bit the cyclical component of unemployment. This is just the same what we are talking here about in global economics, about the potential output and the output gap, and that this famous economist Arthur Okun, that he estimated made an estimation, and that he found that, not very surprising, that we have a qualitative inverse dependency between unemployment rate and economic growth, just explained by the business cycle, but that this dependence is not one-to-one, that more or less if we have a growth rate of 1%, then roughly for developed economies, or especially here the United States, unemployment is falling only by half of this amount, by 0.5%. And this we explained in general with some frictions in the labor market, and also with this general technological improvement, that with the same time, if we have technological progress, that with the same time we can provide more goods and services in the future. And then if we write down this empirical finding, that in the end we have in general this dependence, where the estimation then found here parameter of 2, and that in the growth version we also find here somehow a possibility to get out of this dependence between unemployment and economic growth, a possibility to get a number for this hypothetical concept of potential growth. And then this was a pity that I haven't looked up where can I find the data just before the lecture, and since the database changed their provision, how they provide the data, I have to admit that I haven't found the right labor market data. But in the end, yesterday then I tried in the evening to find the right data, and even this was not possible for me, because the first point was that here, just downloading the non-cyclical component, this is just the topic in my lecture today in macroeconomics. This is definitely the wrong data, because this is then the non-cyclical component. So it isn't the actual data, the fluctuating data, but this is just the long-term trend. So this is definitely wrong. But then I see here, this would be then in general the right data, seasonally adjusted, but then I have the problem of the frequency of the monthly frequency, because the data which is provided for the GDP growth, there I have quarterly data. And yeah, then I tried a little bit to change this frequency, and actually I didn't found it. And yeah, actually, when I was working for the German Council of economic advisors. There are, of course, many tasks for me where to find data and to show it and to show dependencies. And there I also had quite often the problem that the format of the data didn't fit what I really needed. So in general, then your task, and this is, I recommend, really a competence which you should learn. First, this you should do in your term paper to find the data and then to manipulate the data so that you can really work with it, that the data is in the right format. So, pardon? Yes, because then I also thought, okay, I go here a little bit deeper directly in the labor statistics. Here I find 820 time series of the unemployment rate. There was my hope that I find quarterly data. But actually, I went through it yesterday in the evening and I didn't find it. And therefore, well, I only get the monthly data. Of course, by hand, I can then create the quarterly data out of it by just adding up 3 times the unemployment rate and dividing it by 3. But doing this by hand for a time series starting in 1984 takes you half a day. And since I had this problem 10, 15 years ago also, then I thought, well, somehow within Excel there should be the possibility to easily change the frequency. And then I found, to my surprise, that there is no possibility. And therefore, then I wrote myself, or I created myself, a possibility within Excel just to change monthly data into quarterly data into yearly data, calculating different averages. And yeah, this old tool which I created 15 years ago, this I just used now, and this I will show you. And this is maybe also a good example that you do not stop there and say, well, I cannot do it because the data is not in the right format, that you just have then some idea how can I go further. Okay, so then let's download this. Pardon. No, there we are. And this one. This is unfortunately now our monthly data. And then some years ago, where is it? This is my little tool which I created, and here I just add up all quotas. But then you have, and this is the problem then in Excel, if you do this, then you have always these two cells, and you cannot directly then reread this data as a quarterly time series, and therefore you have then to use some possibility you have in Excel that in the next sheet you read only every third cell into the new time series. And maybe if you are interested, I will provide to you also this tool, and maybe somewhere else in your bachelor thesis you have the same problem, then you can just use it. So, okay, because yeah, my colleagues 15 years ago, they said then, well, we are using a special software package, statistics software package, where you have just in the menu the possibility to change the frequency. But sometimes you don't have these special software packages. And this was also my recommendation that you really start to use all the possibilities which you have in the standard Office packages, because this you will have later on when you start working. Okay, so we copy this data and plug this in. So this is then just the sum of the three numbers. And now I read in the next sheet only this, this, and this. And since I want not the aggregate, so not 3 plus 4 plus 7, but the arithmetic mean, this I did just here by dividing by 3. And, oops, then this would be the quarterly data, and then let's go to my data file for this lecture. This were the real GDP measured in chained US dollars, and here then the unemployment rate, and this is starting then from the first quarter. Oops, here we are. Oh, okay, then going to quarterly data, then of course that the last data point is the right one. We see here that the last data point is fortunately just August, and therefore the aggregation for the second quarter is also okay. But if you would have only data until June or July, then of course you have not a full data point for the last quarter. And this you always also have to keep in mind, that you look at the starting point and at the end when you are changing the frequency. Okay, but then let's until the second quarter. Oops. Starting 48. Ah, sorry, this is the wrong Excel file. This we can close now. No, and here from 1948. Ah, shit. Again, copying and no, then I have to fill in just the values because now it's a formula. Up. So now we have it. Let's look if it ends. So for the last quarter where we have already the unemployment data, we have no data point for the economic growth rate. This we have then also to keep in mind creating our diagram. And then what we wanted to do is the yearly change. No, this is again the wrong one. GE. No. Oh, yeah. So the yearly change of the unemployment data, this minus this, and the yearly change of real GDP growth rate minus 1 and until today. And this we don't need because we have no data for the unemployment. And then hopefully now it looks better than my picture from yesterday. Yeah. So, and here you then nicely see this, oops, negative dependence. Missed again, sorry. Plug in. And now let's move this upward, that you find it later on when you download. One last try. I'm not able to copy some file. Now it worked. And yeah, be also in your term papers careful to provide the names of the axes, because right now we don't know which is which. And this would be then jobs, economic growth versus change in unemployment, and the axis. Let's go at first in the data that we are right. So the horizontal axis is the change in unemployment, and the vertical axis is the change in GDP. So this is then dy over y, and this is the change in unemployment. And the unemployment is in percent, since I haven't divided it by 100. Okay, then let's put in, this is more or less the same because this was the picture from last year. But in order that I provide you also the right one. Oops. This we want, this we want, this we want, and skip the rest. And taking this. Yeah. And so in general, we have there, where did I put it? Here, our dependence of if we take this formula, how do we show this? Now here that we have gy is a delta u plus gy star. These two are our data points. And these are our parameters. And now I want you in general show you the linear regression, but this is then the end. In general, we could say that gy we would define as a parameter y, the dependent variable. Delta u would be then our x, a still a, and gy star would be b, and then you end up with y equals ax plus b, and this is our linear regression equation. But I will show it to you in general. But I ask in your introductory course, you haven't done the linear regression, and again in school sometimes it is done, linear regression. If not, it doesn't matter. So then let's talk in general about linear regression. So maybe in some other course you are given some data, and here I took the example that we have the data of the sales volume in some year, and then we think, well, there is always a guy going around and asking, do you want to buy my things? So it is just ringing at your door. Sometimes it is still done that somebody is ringing at your door and wants to sell something to you. And then maybe the company has the idea, if I send more people outside doing these visits, that then maybe I can sell more. But in order to get an idea, is there this dependence? The manager looks into his data, and then he found, well, in 2008 we had 9 visits, and this has created a sales volume of 24 euros. In 2011 we had 13 visits, and there we had a sales volume of 29 euros. And now you think of the idea, would it be a good idea to increase in general the number of visits? Actually, maybe to hire a new person, to increase this of to the number of 30. What can I then, out of my historical data, expect? What would be then maybe the new sales volume? Well, and for this, let's also look at this data, and a first good choice would be always just to have a look, how does it look like in a diagram. But now I cannot copy it anyway. Let's do it like this. Visits and sales 2008 and 924 1133 924 1133 510 13 29 20 42 and 12 24. Yeah, again. Oops. Let's have a look. Well, and just by eye, we see, well, maybe there is some positive dependence that more visits are creating more sales, but now we want to do a quantitative analysis. So what would be a good fit explaining these dependence between these two variables that we say sales is depending on the number of visits. And in the end, here we want to make a forecast for the 30 out here. Okay, so in general, then we say, as I said before, visits is then our dependent variable, and X, no, the other way around, sales is our dependent variable, and X is our independent variable. And with this X, then we say that we explain the development of Y. And in general, a change of X will implicate a change of Y. And now we make the hypothesis that we have a linear dependence. So hopefully in mathematics you have talked about linear lines. This is one general possibility, that you have a linear function 3 plus 2 times x. Do you remember how does this function look like? F of x, 3 plus 2x. What is the 3 and what is the 2? Yeah. Yes, the vertical axis. So we start with at 0, at 3. Yeah. Yes, the 2 is a slope. So going one step on the right means I have to go 2 steps in the vertical direction. So then maybe this line looks like this. Or in general, if I say I have 2 parameters, a and b, then in general f of x could look like this, or it could be also a falling with here we have ab larger than 0. Here a is larger than 0, but b is smaller than 0. And we could move this, of course, also in the negative part for a. So this would be a smaller than 0, b larger than 0. And here we have a and b are smaller than 0. Well, and then we want to think about the question, which kind of linear line fits, so to speak, best our data, which we had here. We just want to include in this diagram a so to speak good linear line. So, and for this, then we make our estimation. What do we understand by a good fit? So this will be then in the end again an optimization program. So the regression line would be then our hypothetical y value, because let's take this just here. Let's fit some linear line by I. Maybe this one would it be. Then of course this was, I think, 13. Did we had such a data point? Yeah. So this was 13 visits, and this were sales of 29. But then the hypothetical data point using our fitted line would be a little bit above. So this would be then y hat of x equals 13. So this is our estimated point. Yep. Yeah, but we want to know what is the hypothetical point due to our fit, which coincides with 13 visits. Yeah. So this is the data point lying on our regression line. And so to speak, how good is our regression would then just mean we compare this hypothetical point with our actual point. So, and then in this case, maybe if this would be 30, then we can say the difference, so our error is just 30 minus 29. Because then we are comparing, this is my data point, this is hypothetical. So this is the theory, and this is the data point. And then the difference between these two, this is just our error of our model. This is the error of the model. And of course, then somehow we want to minimize in the end the sum of all errors. And there, in general, we use not the sum of all errors, but we are squaring all errors. And this then means minimize the sum of all squared errors. And this, I think, you have already seen in the introductory of your statistic course, that you can compare this. There you have calculated xi minus relative to the average squared I equals 1 to n, and this you have called the variance. Yeah. So this was your so-called second moment of your data set. The first moment is the average, the arithmetic mean. The second moment is then the squared summed difference with respect to the average. And now is my question, how did you motivate that you choose here just the squared sum? Have you talked about this, or was it only said? Yeah, this is a good reason, because here if we would just take the sum, here we have a deviation upward, here we have a deviation downward, and if we would just sum it up, then they would cancel out with each other. And in the end, we are with a very small number, although the data is fluctuating quite much, and squaring this number would then just mean that a minus sign becomes a plus sign. Okay, anything else? Because this we could also do if we would choose just the absolute value of the difference. Why don't we use it, this form? This would also do the job, that a plus, a minus is an becomes a plus sign. Or why don't choose xi minus x bar to the power of 4? This is also doing the job. Or to the power of 8. Yeah, every even number would do the job. Yeah. No, the other way around. This square here has much to do with the standard deviation. So maybe the first thing, how we can motivate it, if we look now afterwards here, now we want to minimize the sum, and then using the absolute value, if you hopefully remember how looks like the function of an absolute value. And how looks the square? How does it look like f of x is x squared? This I would also recommend that in your head you have some graphs of functions, and one is of course the linear line. The second one would be f squared, square root, the log, or the exponential function. And if you know how, and 1 over x. And if you know how these 5 functions look like, then you are more or less done in economics. But it would be a good idea. So f of x, the absolute value, is on the right side. It is just f of x. So it's the linear line with slope 1 coming from the origin. And on the left side, it is just mirrored at the vertical axis, because then it is just the function f equals f minus x. So this is absolute value. And if we say here is 1, 1, and minus 1, then we also know that f of x, x squared in 1 is also 1, and this is a parabola which looks like this. Well, and then we can say there is a technical reason why it's nicer in optimization problems to use the squared and not the absolute value is just this point here. There the function is not differentiable, because the left side first derivative is minus 1 and the right side first derivative in the origin is plus 1. And the parabola, this is differentiable. There the first derivative is just 0 in the minimum. So f of x equals absolute value is not differentiable in f of x, in the origin, sorry. And optimizing, maybe you know it is always nice if you can calculate derivatives and setting them to 0. And if there is no derivative, then you have a problem. And yeah, and then you already mentioned the normal distribution. And do you know how the normal distribution, the function for the normal distribution looks like? Yes, this is this Gaussian curve. And how does looks like this function, this density function? How can I describe this this graph? Well, this was 1 over square root of 2 pi times sigma squared. This is the standard deviation times exponential x minus mu over sigma squared. So this was your expected value and this was your standard deviation. Again, then I do it a little bit larger. So f of x is 1 over square root of 2 pi sigma squared exponential x minus mu over sigma. Well, it's much larger, yeah, I'm sorry. So mu is the expected value and sigma is the standard deviation. Well, and here in the normal distribution, density of the normal distribution, here you also see this fundamental distribution function, which we find almost everywhere in nature and in the data, that this function is also described via this squared distance. And there is a last point which we can say that using the squared distance creates also a so-called maximum likelihood estimator. But I don't think that you have already heard about this. Maybe later on when you are doing some econometrics or something like this. And so in the end, there are some good reasons in order to use this squared distance. But on the other side, there is no law that you have to do it. And always you have to look at your data and looking, is this a good version, is fits this really my problem? And for example, maybe one of you is later on choosing also the topic. I don't know if you will hear also the lecture in financial economics or international finance or something like this. And then you are looking at financial data. And there you see in general that assuming that your financial data is distributed due to the normal distribution, underestimates the outliers. So unfortunately, a financial crisis happens much more often than the normal distribution would say. And therefore, then in the financial data, you still use quite often the normal distribution, but only for an approximation. And Sometimes if you have a deep look in your data, then it is maybe better to use this absolute value, although it is a little bit more complicated than the squared due to this problem of the derivative in the origin. And this is then called the so-called Laplace distribution, but it fits better your data. And to my opinion, unfortunately, sometimes we only say, well, we use the square because of this positive and negative sign of the distance. I think this is not enough in order to explain why do we almost always use this variance form with a square distance. Okay, but now hopefully I have motivated a little bit why we want to use the quadratic difference. Well, and now we have a standard optimization problem because we want to minimize just this sum. But then this is our data point. We can plug in our hypothetical point on the line. And this point is depending on just two parameters. So keep in mind these two numbers here, all xi, x1, x2, x3, x4, and so on. These are the numbers you know. This is your data. So you end up with a function just depending on two parameters. And how can we optimize or here minimize a function depending on two parameters? Pardon? No, this is then the result. We want to come to the linear regression. Now you have to go a step behind and you have just any two parameter function and you want to optimize it. What are you doing mathematically? I think all of you have done already micro, or? No? What have you done in microeconomics? There you had this funny picture, x2, x1, budget line, and indifference curve. What have you done then? Yeah, you did the Lagrange function, and then you had a function in general depending on x1, x2, and a new parameter lambda. So there you have three parameters. No way it's analytically the same. And what have you done with your Lagrange function in order to get the household optimum? Yep. Yeah, but at first you did here just all partial derivatives. You took the derivative with respect to x1, x2, and with respect to lambda, and then hopefully your utility function looks like this, that you really can solve this non-linear problem. So here we have to take the partial derivative with respect to a. How does the derivative look like? Well, maybe if you have not used this summation sign that often, then just think of this looks like y1 minus a plus b x1 plus y2 minus a plus b x2 and so on plus yn minus a squared, sorry, plus b x2. And here you have to take the derivative with respect to a. Of course, these are all fixed numbers if you take the derivative, because this is your known data. The derivative of a fixed number is 0, of course. So we can skip this. Then we have still this minus sign. And what is the derivative with respect to a of a plus bx1? Again, x1 is now just a fixed number for you. Yeah? Yeah, great. 2a plus bx1. So this you have to do for every part. You are summing this up. So you can then just write a summation sign in front of this. I equals 1 until n. And what is the condition of the first derivative in order to get an optimum? Equals to 0, of course. And then f of ab with respect to b. What is the derivative with respect to b? Huh? So if you just look at this part here, a plus b times x1 squared. This is your function. Let's say this is a function now only depending on the parameter b. In our head, we now use also a as a fixed number. What is then f prime? Yeah, and what kind of rule do we have to apply? Taking the derivative? Because here you have an inner part. You have still a dependence within this bracket, and then you have to apply the so-called chain rule. So f of g of x, then with respect to x is f prime of g of x times g prime of x. And the inner function is b times x1. B times x1, the derivative with respect to b. I think the problem always here is that you always think in your head, although you know you shouldn't do it, that you always want to take the derivative with respect to x because you have done it so often in school. And yeah, I have to admit, I see it when I look to my kids when they go to school and what they are doing there in mathematics. And just to learn how to deal with these letters, with these parameters. And then in the end, it doesn't matter if it's called X, Y, N, M. This is, I think, never really explained to our young people. Yeah, yes, I think this is really the problem because what you have to do here, if I rechange the variables again, that you can take the derivative with respect to x, then f of b equals b times x1 is the same if you look at another function, let's say f of x is 3 times x. Yeah, because this x1 is just any number for you. This would be then, in the context above here, your 3. And f of x equals 3x. The derivative is the derivative of this function here. Pardon? It's 3. Now we are taking the derivative with respect to x. And here, now we switch it. So here, the derivative, this wouldn't be b. We are taking the derivative with respect to b. So we end up just with x1. So here, times inner derivative times x1. So overall, we get again 2 times a plus b x xi times xi equals to 0. Well, and what we, oh, this has also to be an I, sorry. And now what we have here is, again, be careful with respect to these two variables a and b, both functions are linear functions. With respect to a and b, both derivatives are linear functions. And what we have here now is we have two linear functions, two variables, and for such a system is just a system of linear equations with number of equations equals number of variables, and there we know that we can in general solve this problem. So system of linear equations, and this we can solve for a and b. Yeah, and don't be too much surprised. The solution of this system then looks a bit horrible. So if you do now all the calculations, then you end up that the parameter a is just this term, and the parameter b is given by this term. And the nice thing is that the two averages of our y-distributed data points and of our x-distributed data points, here the arithmetic means of these x and y values is also always situated on our linear regression, on your linear regression line. This we can also show. So this means that if you have calculated just the parameter b, then you can directly plug it in and you can directly calculate your parameter A. Okay, and I don't know, maybe in your statistic course you have also talked about this so-called covariance. Have you heard already about this? Because here we can also show that the parameter B is just the covariance divided by the variance of the parameter of the values of x. And you see here covariance is somehow defined in a similar way like the variance, but only we do not calculate xi minus x bar times xi minus x bar, but we plugging in here yi minus y bar. Maybe we see it somewhere later on, the term covariance, yeah? No, not coefficient. This is covariance is just defined as the product of both linear differences of x and y, as we have done it here below. Okay, some minutes are left, and then we can do the linear regression. So let's take now our data and, oops, if we look especially in the calculation of B, then we see, okay, we need the sum of all x, we need the sum of all y's, we need also the sum of the product, first multiplying just x1, y1 plus x2, y2, and so on. And what we also need is we need the sum of the squared of x's. So this is x1 squared plus x2 squared plus x3 squared. And here we have to first take the sum and then the squared. So these are not the same numbers. I hope that you see this. So then this means if we have our data, we can just add these numbers up, this we need, and then we just calculate the product and we calculate x squared. And this we can then also sum up. Okay, let's do this. Where do I have it? Here. So this was x and this was y. And then let's take calculate xy and x squared. And this can, of course, directly be done. So we take 9 times 24. This for every pair. Oops. Copy. And also the x squared. So equals x squared. Copying this down. And what did we needed? We needed all sums of these columns. The sum is then this need for every column. So, and can I see this here? Sorry. Up. Here we are. This one. So n is the number of our data set. We have 6 years, so n is 6. or this is I. So I, and then we have n equals 6. Yeah, and then we have just to apply our formula. So B is equal n, this is our 6, times the sum of the products. This would be 2134 minus the sum of x is 70. Yeah, great, go on. Times. No, yeah, first multiplied by 162 and then divided overall again n 6 times, yeah, x squared minus, no, here's no n. Be careful, no n. It's all, yeah, 70 squared. Great. 70 squared, and this is our b. I will just write it down also on the slide in a minute, yeah? Well, now we could also, oops, apply this horrible function here. But if we know that the averages are also lying on our linear line, we can just apply this one. So let's calculate x y bar and x bar. So here, this then we have just, let's say the average. We obtain this by 70 divided by 6. Okay? Up. 70 divided by 6. And of course, y bar is 162 divided by 6. So 162 divided by 6. And then let's move on the other side. Or this is possible. So then we obtain A equals y bar 27 minus B, this we have already calculated, 1.97 times x bar 11.666. And we have our 3.981. Yeah, 70 by 6, yeah. Mm-hmm. So, and in order to show our regression line, now we are calculating the hypothetical values. So what would be due to these parameters A and B? The hypothetical volume of sales if we make 9 visits. So this I then call y hat. And this would be then y is A, and in order that I can copy this, I have to put dollars. I think this was possible like this. No, right? Then let's do it by hand. If I put in front of, I don't know if you know this, because I want then downward copy my formula. And so this would then fix my parameter A times X. Oh, sorry, it is the other way around, no? B is my slope, sorry. How did I, yeah. A is my vertical axis and B is my slope, so it is X plus B times my X value, and this is, oh, something wrong here? There. Now it functions. So we had an actual value of 24, but our model would predict it would be 21.7. And now we can copy this downward here. Oh, this was too long. And let's put in this data also. This would be then X values are the same and the Y values are the calculated ones. So this would be then our data which we need here. Again. Oh, oh, sorry. Adding X values and Y values. I've forgotten to click OK. So that you can later on see this. Let's take this and hopefully this works. No. Yep. And then we had here the sums. This was 70, 162. Yo, thank you. 90, 40. Then we have X bar was 11 point and 27. And here we had 6 times 2134 minus, yep, yes, and this was roughly 1.97, and this was then y bar minus bx bar equals 27, yep, was roughly 3.92 or 92, yeah. So what says the clock? What time is it? Oh, there's still some left. Yeah. So this is a linear regression done by hand, and now think that you have a huge data set. Then it's not very funny to do all this, and for this you of course have here also the formulas directly how you can calculate this, and B was the slope, and well, I don't want always to switch to the English version of Excel because then I also have the problem between comma and dots providing the data and so on. But then you have here the number uh, in German. So the German word for slope is Steigung. And then you just see what you have to do. The first one are the y values to feed in, and the second one are the x values. So these are the y values, and here we have the x values. Hopefully, enter, I get a 9.1.97. And this is the vertical part. So this is called Achsenabschnitt. Again, plugging in the y and plugging in the x part, and you end up with your part here. And just like this, you can calculate then later on also for your time series your linear regression, because what we want then in our time series analysis just to somehow fit here the best linear line through this data cloud. But I will then also do it for you for the data set, which you should do in your term paper from 1980 and using the IMF data. Okay, 5 minutes left. Let's see. Yeah, in general, what we have done here now is that we have fitted in our theoretical linear line, and this linear line minimized all these red squares and the sum of this, so the area of all these red squares. And to sum up this, that in general we have our regression coefficient B, and this is the most important one because this is the slope of the linear line, and so this defines your dependence. So if my x value is changing by 1 unit, then I know how much is changing my y value. And for this, in the end, then we wanted to know what is, from this estimation, my expectation for sales when I make 30 visits. Then what is the expected sales volume for x equals 30 visits? This is my last question for today. What do I have to do then? Well, we have calculated our A and B. This was our, where are we here? We have y hat I equals, and this was 3.92 plus 1.97 xi. Oh, not bar, but hat. Yes, not more. And then y of x equals 30 is then 3.92 plus 1.97 times 30. And let's do it here. Y of x equals 30 is then this plus this times 30, 36.72. 33.21. Well, and this is then, so to speak, your estimation. And then you say, well, out of my historical data, I have now the expectation that if I hire a new person, increasing with this hiring the visits, this will increase my sales volume to 33.72 euros, and then you can think of yourself, this this guy is of course also costly. Can I finance this guy out of this increase of my sales volume? So of course this is a very simple example, but in the end just this is done in your companies where when you make your forecasts, where are going my profits and what should I do. Okay, then next week we will add another point, because if you look at this, this calculation we can do just for every data set. You always will find some line which fits due to the optimization, the the square distances, the sum is minimized. But then, of course, you want also to have some idea, well, how good is my fit? So is it really reasonable? Because this you can do for every data set. You don't get out the information, is it good? Is it reasonable to do this or not? And this is then done in the so-called correlation analysis. The R squared maybe you have already heard of this, the coefficient of determination. This we will also then next week calculate for this little example, and then I go through a one-time series analysis as a whole for you. And yeah, then that's it for today. Thank you very much.